Welcome, everyone. So glad you're here. Today, we're diving into a really fascinating explainer. We're going to demystify exactly how we build robust, powerful software from the ground up. You know, if you've ever found yourself wondering how these massive, complex Java applications are actually structured behind the scenes, well, you are in the perfect place. We're going to break down the 4 foundational principles of object-oriented programming, or OOP, in Java. We'll see exactly how these principles take what looks like abstract lines of code and totally transform them into intuitive, real-world models.
We're going to construct our knowledge today pillar by pillar. Our agenda is simple. First, everything is an object. Second, encapsulation. Third, inheritance. Fourth, polymorphism. Fifth, abstraction. And finally, number 6, the pillars of robust code. Let's just jump right in.
Section 1. Everything is an object. Modeling reality in code. Okay, so this is the core philosophy of object-oriented programming, right here. We are literally modeling reality in our code. Take a smartphone, for instance. In the real, physical world, it has a specific state, like its current battery level or the apps you've got installed on it. And, of course, it has behavior, what it can actually do, like making calls or opening up those apps. Well, an object in Java operates the exact same way. It's simply a real-world entity modeled in code, complete with its own state and behavior. And the class? Think of a class like a manufacturing blueprint in a factory. It's the template that defines what a smartphone should be, so we can stamp out as many individual smartphone objects as we need.
Section 2. Encapsulation. Protecting the data.
I want you to imagine encapsulation as a locked box. You hide your really valuable data securely inside it, and you and only you are entirely in control of who actually gets a key. Because think about it, if you leave your data out in the open in some massive codebase, other developers or just different parts of the program might accidentally modify or delete it, and that causes catastrophic bugs that are just an absolute nightmare to track down. So encapsulation means locking that internal state away and exposing only the specific, controlled methods that the rest of the program actually needs to interact with. It acts as a super strict protective shield. So you might be wondering, how do we actually do this in Java? Well, we translate that locked box metaphor directly into our code using some very specific keywords. First up, we declare our data variables as private. That is essentially putting the lock on the box. It means absolutely no outside class can touch this data directly. Then, to allow for safe interaction, we provide what are called public getters and setters. These public methods act as a heavily controlled gateway. They are literally the only way in or out of the box. You ask the public method to update the data, and the method ensures it's done safely. Boom, your private data stays perfectly protected.
Section 3. Inheritance, sharing parent attributes.
Now, inheritance is the absolute ultimate solution for reducing redundant code. Let's think about a parent class first. Say, an animal, defined in our code with basic, shared properties, like footprints and a general silhouette. Now, because our child class, let's call it a dog, is an animal, we really don't want to rewrite all that footprint code from scratch, right? That'd be a huge waste of time. Instead, the dog class simply inherits from the animal class. It automatically gains all those shared traits. But, and here's the cool part, it doesn't stop there. The child class can then add its own unique characteristics right on top of what it inherited, like a physical collar or the behavior of wagging its tail. You write the foundational code once in the parent, and you infinitely reuse it in the children. It's a real game changer.
Section 4. Polymorphism. One interface, many forms. One interface, many forms. I absolutely love this phrase. This is where your code gets incredibly flexible and dynamic. It basically means that we can use a single, unified command, but it's going to trigger completely different, highly specific behaviors, depending entirely on exactly which object receives that command.
Let's break down how this polymorphism actually works using some real Java logic. We're going to use the exact same action, or method call, which is soundAction. First, we declare a reference type of soundAction, and we assign it to a brand new cat object. When we call that soundAction method, the result is that it prints meow. Makes perfect sense, right? But now watch this. We take that very same reference, but this time we reassign it to a new dog object. When we call the exact same soundAction method again, it now prints bark. Think about how incredibly powerful that flexibility is. The exact same method produces uniquely different results depending on the object it happens to be pointing to at the time. That right there is polymorphism in action.
Section 5. Abstraction. Hiding the complexity.
Think about your phone's physical power button for a second. What you actually see and interact with is simple, clean, and essential. It's just the single feature you need to turn the machine on. But hidden right beneath it is this totally chaotic, wildly complicated circuit board. You don't need to understand the crazy wiring or the capacitors or the microchips to simply press the button and turn the device on, do you? No way. Well, abstraction in programming does this exact same thing for other developers who are using your code. You provide them with just a sleek, super usable interface, completely burying all those chaotic implementation details deep inside.
So how do we actually build this virtual power button in Java? We use a couple of specific tools, abstract classes and interfaces. By using these, we define essential contracts. We are basically saying, hey, any object that uses this interface absolutely guarantees it will have a power button. We define exactly what the object must do, but we completely hide the details of how it actually does it. And let me tell you, this makes massive code bases incredibly easy to navigate because developers only have to focus on the essential features. They don't get bogged down in the underlying chaos.
Section 6. The Pillars of Robust Code. Reusable, maintainable, and scalable.
All right, let's take a step back and quickly review why these are so much more than just fancy technical buzzwords. These 4 pillars are the absolute core design principles of powerful software engineering. Encapsulation, that's your security guard. It keeps your data totally safe from outside interference. Inheritance is your efficiency expert. It promotes reuse so you aren't stuck writing the exact same code twice. Polymorphism is your acrobat. It gives your code this incredible flexibility to adapt on the fly. And abstraction, that's your designer. It hides all the unnecessary complexity to keep everything looking clean and completely understandable. Together, they literally form the foundation of every major object-oriented program out there.
Now, to make sure you can take all this knowledge straight to your keyboard today, let's rapidly align these theoretical concepts with their exact Java keywords. Step 1. When you want to model a real-world entity, you're going to use the keyword class to define your object's blueprint. Step 2. To protect your data, use the keyword private to achieve encapsulation. Step 3. When a child needs to share parent attributes, just use the keyword extends for inheritance. And finally, step 4. To achieve that awesome, flexible polymorphism, use method overriding so different objects can respond to the exact same command in their own unique way. If you master these steps, I promise you are going to write cleaner, vastly more robust Java code.
We've laid out the entire blueprint today. Honestly, the absolute best way to internalize these concepts is to just get out there and keep practicing by building small class hierarchies and interfaces for yourself. Start small, experiment, see what happens. But before we wrap up, I want to leave you with a question to really think about. Now that you have the 4 pillars, literally the exact same foundation used to build the world's most complex software, what world are you going to build with your code? Thank you so much for joining me on this explainer. Happy coding in Java, and I'll catch you next time.